Welcome to short series video for the AVEVA process simulation. In this video, we will learn about the basic steps to build the simple simulation using the recommended workflow that solve that simulation and view the results. And to check the results, we have a sample example or problem statement so that we can have an idea about this. In this video, we will cover how to handle the mistakes, meaning of warnings, then badges and errors. Basically, this video is useful for the beginner. Those are new to AVEVA process simulation software and they can learn how to develop a new simulation. This video is recorded using AVEVA process simulation version 2024.2. This is the draft about the how we can see the once the AVEVA process simulation software window opens, and I will show that window directly to you. This once you open the AVEVA process simulation software window, it looks like this. To create a new simulation, before to start new simulation, we will just go through the types of libraries available in the AVEVA process simulation. First is process library, then second steam, flare, renewables and cooling tower. Before proceeding to further, I would like to highlight that the process library is the most common library used in the chemical and petrochemical industry. Flare is mostly used in the refinery and petrochemical industry. To create this new simulation, we are going ahead with the process library. Okay, here we can change the library type at the start of the simulation. For now, we are going with the process. Then we have two different tabs like the simulation building that can be done using the existing models available in the AVEVA, and model writing option is for to generate the new model based on the our specific requirements. For now we are moving ahead with the simulation building. Then we can change the unit from here. For now we are considering SI units. Then we can also change the background of the theme like dark, light green, blue. I just show one of that. Once we select blue, it looks like this. So we are going ahead with this background. Also, we can change the background color by going to the custom option and here. Okay. Also, the we can uh, change the size of A4, A1, A2, A3. Basically, the whatever the space available for modeling is called as a canvas, and this is size of the canvas. Okay. This, we are moving ahead with the create new simulation. We can rename it as a simulation 1. We are moving ahead with the process library. Then we can change the simulation manager view that can be required later on, and mini inspector as well. Okay, we have started new simulation. This can be renamed as a simulation 1. Once we have done the renaming of that simulation, we have different types of tools like flow sheet, binary phase diagram, then trends which is required for the comparing different types of parameters against each other. In control section, we have instrumentation parts that can be I will explain in later videos. Economics is the same for the capex purpose or the costing purpose. Then in fluid section, we have different fluids like cooling water, steam, air, whichever fluids we have to use for the simulation purpose that can be available from here. And if there is no any fluid, we can create a new fluid from the fluid creation that can be covered in the later on series. For now in process, we just need to the different types of models are available in this, like source, sink, control wall, drum, distillation column, pumps, heat exchangers, then safety walls, continuous stirrer reactors, and all these things. For now, we'll just focus on the basic simulation generation, and this blank space is called as the canvas. To generate a simulation, we have to just drag and drop the model from here. We have drag and drop the source, control wall, and the sink. Then we can connect them internally like this. Then we can connect once we can connect them done. The badges looks like means some parameter specification is missing. That badges required can be used for the initial period, that can be removed from here also. But badges will give idea about whether that simulation is in not solved stage. Oh, canvas badges meaning if it looks like this, then that means the input required is missing. Here is a warning that sign reflects the not solved stage. Okay, and once it looks like this, that means the complete simulation is in a solved stage. So we are going to add the fluid here, like default fluid. We can select different fluids from there, like cooling water, steam, control default fluid. Here we have select cooling water as a fluid. Okay, then we have one problem statement is there, like feed flow rate is 10,000 kg per hour, inlet pressure is 2 bar gauge, and temperature is 30 degrees Celsius. For this, we have to calculate the CV of the control wall at 100% opening, at 50% opening. Okay, we can change the composition molar to mass or mass to molar. Here we have selected mass flow. Then we can add here elevations and the fluid stage. Here we can add fluid, vapor, liquid, VLE or other whatever the state we can select accordingly. Here we have cooling water, hence I have selected the liquid as a fluid. As per the problem statement, this badges shows the input required, like flow rate, temperature, and pressure. Here I have mentioned 10,000 kg per hour of flow rate. Then we can change the pressure first. There the pressure of bar gauge. We have pressure of 2 bar gauge and temperature is 30 degrees Celsius. Rest are okay. Now it's the badge is gaib, that means it's in complete solve stage. Now we have to uh, input the parameters for select the parameters for the control wall. Here we can check that flow models within process category, whether that fluid is compressible or non-compressible. Here is liquid, that means that is incompressible fluid we have selected here. Then the phase of liquid, vapor, whatever may be the fluid we have selected, we have to consider its phase. For cooling water, we have liquid as a phase. Then we can check other parameters, whether that control wall characteristics, whether it is linear or continuous or equal percent opening or quick opening. Here we consider linear opening. Then the control wall sizing, which is our problem statement, we have to calculate the actual control wall CV size. To do that, we have pressure drop of 0.5 bar. That is already here. Okay. And this is manual wall position. Opening percentage is 100% opening. Okay. It looks in a solid stage. To check that parameters, we have to consider that to drag down these parameter here, we have to select and drag here. We can change the unit meter cube per second to meter cube per hour. That automatically considered here. And this blank box shows the calculated value. For control hole, we have to select the GP here, then manual percentage opening and the DP manual percentage opening there, and calculated value is CV. We can consider here, that is the calculated. We can select all and drag down here. Okay, and we have to same way, we have to just add the flow rate on the sheet. Okay, as our problem statement, we have 10,000 kg per hour of flow rate. For 10,000 kg per hour of flow rate, we have calculated CV of 16. Okay, we can rename its name as a feed, then it's control wall, and it's out. Okay, if we change the wall opening percentage from 100% to 50%, it will directly change the CV value. It goes to the 32%. This is a steady state simulation. Even though we can add the delta P across the wall, that will directly affects the CV value as well. So this is the as per our required problem statement. At 50% opening, we required the CV is 32, and for 100% opening, we require CV is 16. That is the problem's answer. It is in solve stage, and we can check it at the simulation manager as well. Okay, hope you all are understood how to create new simulation, and that can be also printed on the page from here like this. Okay, you can print it as you want in any form. That's it. Hope if you like this video, please like and subscribe my channel for upcoming videos like on heat exchanger design, safety wall sizing, orifice sizing, and the dynamic module of the same simulation which we have done for the steady state here. Thank you. Bye bye.